uh, one cycle, and the ultimate strength. So this is X is one cycle, and Y is S ultimate. And then the second point is 1,000 cycles and a fraction of the ultimate. This fraction is F times S ultimate. In other words, if we know the ultimate strength of material, then this fraction can be worked out. This fraction, there's a graph in the book that shows F as a function of the ultimate strength for steels, and it starts, when the strength is 70 MPa, then it's 70 KSI, it is 0.9. When the strength is 200 KSI, it is 0.75, and you have that relationship in the form of a graph. So once we find F for a given strength, then we can determine the Y coordinate of the second point. The third point has a coordinate of 1 million on the X and endurance limit on the Y. And the endurance limit is a fraction, again, one other fraction of the ultimate. So the story starts with the ultimate. You take a fraction of that, F times S ultimate, to determine the boundary for the high cycle fatigue. You take another fraction of that to find S endurance. The S endurance usually is half of the ultimate, so the second fraction is 0.5. But the first one, F, can be between 0.75 and 0.9, depending on the ultimate strength. Having done that, then we can determine the equation for the straight line. So this equation for the low cycle fatigue is SF, which is the fatigue strength, is S ultimate times the number of cycles failure raised to the power B1. And then for the high cycle fatigue, it's SF is equal to a constant A times the number of cycles to failure raised to the power B. Those okay, so this is B1, and A and B are three parameters that can be determined from these coordinates. So once we know the coordinates. And here it is. So A is given by this equation, Fs ultimate square over Se. B is given by this equation, and B1 is given by log F over 3. So that's a complete recipe now for fatigue design based on the SN method. It's a summary because I have the my full lecture online. So this is a page of the summary. Now what we want to do is I want to apply that to show you how it works in an exam question. But before we do that, I'm going to add one more thing. So here is another consideration for fatigue, and this consideration is that if the amplitude of the reversed, just get my, so you can see. If the amplitude of the alternating stress is not fully reversed, in other words, we have another mean component of the stress, then we have to take that into account. And the way we take it into account is through two damage fractions. One fraction that relates to the mean stress, and then another fraction that relates to the alternating stress. So when we add up the two fractions, we get 1. And these are the various relationships that you have in the lectures. Soderberg, the fractions is S alternating over SE. So this is the alternating, it relates to the endurance limit. The mean relates to the yield strength. These are the maximum values for the alternating and the mean stress consecutively. And if we have a design factor of safety n, it will be just 1 over n. The fraction is 1 over the safety factor. So Soderberg is the mean is related to the yield. Modified Goodman is the mean related to the ultimate. Gerber is the mean related to the ultimate square. The ASME is the mean related to the yield square. You have these relationships. So if we plot all of that, we plot them on a graph, two-dimensional graph. On the vertical, we represent the alternating stress, and on the horizontal, we represent the mean stress or the steady stress. And you have a whole bunch of lines, as you can see here. The one I'm going to try try to see if I can point effectively here. So this line, for example, sorry, yeah, I can't do that. So this line, this line goes from S endurance to S yield, and this is the Soderberg line. It's a straight line equation. The Gerber is a parabola, so it's a parabola right here, and it goes to the ultimate. And the modified Goodman is a straight line. It goes from S endurance all the way to the S ultimate. So it gives you more of a design margin than Soderberg. And the ASME is an elliptic equation that goes from S endurance to S yield. So we've seen all of that in the lectures. Now, what is the new idea here? The new idea is that we have to consider two additional lines on there. One is called the load line, and the load line is a relationship between the alternating component and the mean component of the stress. So S alternating over S mean, that's the slope of the line R, and it goes a straight line like this. And of course, we have to make sure that the design point is inside any of these four different criteria, depending on how conservative we are or how much we want to push the design margin. So if I have a point right here, then it will be safe. If it is right there, then it will not be safe as far as Soderberg is concerned, but it will be safe as far as the ASME and so forth. One additional line is the line that goes from S yield on the vertical to S yield on the horizontal. This line, the meaning of this line is called the Langer line. And the Langer line, the meaning is that at any combination of alternating plus the mean, you shall not exceed yield, because we know that the total stress is the mean value, and then you add to that the alternating value on top of this. So if you have a cycle, for example, the first cycle you will have the mean, and then on top of this you have the alternating. If that exceeds the yield, then we got trouble right from the first cycle. So the Langer line is a line to protect against yield on the first cycle. So to determine the safety factor and to determine whether we will have yield on the first cycle, we have to get the intersections of all of these lines. So every point, like for example, the load line intersection with the Soderberg line, you have coordinates X and Y. The load line with the Langer line intersections X and Y. The load line with the Gerber parabola is X and Y, and so forth. So all of these intersections, of course, if we have the time, we can do the algebra. We can just solve the equation of two straight lines, or a straight line and a parabola, like what we used to do in high school. But for us, it is done for us. In the book, we have a table, and the table gives us the coordinates of these intersections. And from there, we can determine the safety factor. So here's an example. In the intersections, you have, we solve the equation. This is with the modified Goodman. We solve the equation R equals SA over SM. That is the load line, together with an equation which is the modified Goodman, SA over SE plus SM over S ultimate equals 1. We get the results for the X and Y. The Y is S alternating is given here, and the X is S mean is given here. And once we get those, then we can determine, let me see, and let me just make sure that I'm recording. Yeah, I'm recording. So we have, these are the intersections we have, and then we can use them to determine the factor of safety. For example, the factor of safety here would be given, so the calculation of the factor of safety, if I want to calculate the factor of safety, then let's say the design point is right there where you have the arrow right there. Then I need the intersection with the Soderberg line, and the intersection would be given by the coordinates. So I have the coordinates of the intersection. So the ratio of any length, like the ratio of this length divided by the design point, is going to give me the safety factor. And I can do this ratio on the straight line itself, or on the x coordinate, or on the y coordinate, because everything is proportional to each other linear relationship. And that is given by here analytically also. So the factor of safety in this case is worked out, and we have, for example, I'm just trying to move that, yeah. And the factor of safety is 1 over SA, sigma alternating over SE, plus sigma mean over S ultimate. So that's kind of the, these are the two key ideas. One idea is how to construct the SN diagram. I have to figure out whether I have low cycle fatigue or high cycle fatigue. Second idea is how to protect against failure on the first cycle, and how to determine the safety factor considering the intersections between load line and the criteria lines that we talked about, and also with the Langer line. So now I go to the exam. The final exam last year, first, if you see it here. So we have something similar in structure for the final exam this year. And you have 5 questions, and it will be open book, because on the midterm, it was your own notes, because the amount of material was limited and the number of equations was somewhat limited, and it was more analytical, more strain type things. So it was closed book. The final is going to be open book, because as you could see, after the midterm, we started having more and more equations for design. So we're moving from why to how to. So now how to design, and that requires a lot of design procedures and equations, and that we have in the book. So we have to be kind of familiar with these procedures. So it will be similar to that. And if you have an electronic version, you can use your laptop, but you cannot use any solution manual. And it's kind of important that this is followed. So if we skip those, I want to just go to the fatigue problem. So in the fatigue problem, here on the final, I have a shaft. So the fatigue is applied to the shaft design, because this is a kind of a key focus of the course, is a design of power transmission systems. So if you can see here, I have a shaft, and the shaft is machined from IC 1040 steel, cold work steel. The shaft is rotating at 2000 RPM, and is supported in rolling bearings at A and B. So we have A here and B here. And then we have gears. So the gears transmit forces. One gear is located at 8 inches from the left bearing, and then another gear is located at 8 inches from the right bearing. And we know that there is a relationship between the gear force F1 and the gear force F2. This relationship is F1 is equal to 2F2. So what is required is that we want to determine the allowable design values for the gear forces F1 and F2. to achieve a fatigue life of 20,000 cycles. And we want to use a factor of safety of 1.5. So if we think about this problem, number one, I need to figure out what does it mean to have 20,000 cycles. So in this case, it's obvious that 20,000 cycles is above 1,000 and below 1 million, so it is in the high cycle fatigue. And if it is in the high cycle fatigue, I need to figure out what is the alternating stress. If I know the alternating stress, then I can kind of think about it and see how many cycles it would lead to, you know, how much is the alternating stress that corresponds to 20,000 cycles. So in order for me to find a relationship, I need to find a relationship between S and N, essentially. What is S equal, what is the relationship? As we've seen in the summary, in the intermediate range, which is high cycle fatigue, S is equal to A times N to the power B. So I need to figure out what is A, what is B, and now in the design world, there might be more complications. Complications would be what is the fatigue factors? What are the fatigue factors in this for this shaft? Fatigue factors, we know that we have like the endurance limit or the fatigue strength is reduced as a result of machining the surface, as a result of temperature, as a result of size. So there's 5 or 6 factors that you have in the book that might need to be determined. Also, additionally, if we are interested in fatigue, let's say at the shoulder, then we would need to figure out if there's stress concentrations there. So the issue of stress concentration would be of importance. And then if I go to stress concentration, then it raises the question, is the stress concentration factor in fatigue the same as the stress concentration factor in tensile or uniform steady loading? And the answer is no. The fatigue stress concentration factor is better. In other words, it is less than the corresponding value in steady loading. And how much better, how much less? The relationship is through the notch sensitivity factor Q. So you can see now a progression of things that start from a very simple idea all the way to the final design. And that's what we're trying to emphasize in this part of the course, is how to do it. So first part is going to be statics, because I need to figure out what is the maximum moment, and where, I mean, the shaft is right there, so I need to figure out what is the critical point. You know, I'm not going to design it for everywhere, but I'm going to have to choose a critical point. So if I investigate this, the critical point would be, it has to be kind of a maximum moment and also a minimum shaft diameter. If I find this combination, then I will figure out the critical point. So if you investigate, all of this is okay. The maximum moment will have to be between F1 and F2, because the moment is going to rise from here to here, and then maybe rise again. Actually, F2 is less than F1, so it's rise a little bit slower, and then we'll fall down again to 0. So this is now we have experience in moment diagrams. So before I get the moment, then I have to form an idea. So this idea would tell me that the worst case scenario is going to have to be between F1 and F2. And since this region is wide, like I have 1 7/8 of an inch diameter shaft, then it will have a higher moment of area, polar moment of area, and therefore I can conclude that the worst point is going to be between F1 and the shoulder. since the shoulder will have a stress concentration factor, then my conclusion right away is that this is going to be the worst case. It is exactly here where I have a shoulder. So I got to do first the statics. Once I get the statics, I get the moment. Once I get the moment and I figure out where I want to have this moment, I can compute it right here. Everything will have to be in terms of F1 because I don't know F1. So I just keep F1 in the equations, and my moment will be in terms of F1. And then the alternating, okay, now the shaft is rotating. So it is like a rotisserie. So on the top fibers are turning around on the other side of every rotation. So the top fibers, some part of the cycle will be in tension. When they come back down, there will be compression, and therefore they will experience an alternating stress. And the alternating stress is the value of the M times C over I, because that's the stress that is caused by the moment. So in this case, I'm almost there, ready mentally. So now I can write the equation for the balance of moments at point A. I take the moments about A, and then I take the balance, vertical balance, I get the forces. And I think all of you can do this step pretty easily. Then now the next step is that I concluded where the moment I would like to have the moment. It's at x equals 10.5. 10.5 is 8 here, and then I add this part here. This will bring me this 10 inches from the shoulder closer to the roller bearings, and then half an inch into the roller bearings where the force is where the reaction is concentrated. So 10.5. So I would just multiply F, the force here, RA times 10.5 to give me the moment. So I don't even need to construct the moment diagram, but I just figured I could do that. So this is the moment is you have 10.5 times RA minus F1 times 2.5, you get 12.5 F2. So we'll keep everything in terms of F2. And sigma now is sigma REV, and that's, as in the lectures, this is the equivalent fully reversed alternating stress. And in this case, we don't have any steady component because we have only alternating. The shaft is rotating. There's no additional torque on it that can make it steady. So it's a little bit easier. So you have alternating, and therefore the fully reversed stress is the same as the alternating stress. It's MC over I. So in terms of F2 is like here. Then the fun starts in terms of determining this A and B and factors in the SN relationship, and in terms of finding the stress intensity factor at the shoulder. So it's all about tables. You have to be familiar with those. Table A20, we get the ultimate strength, 85. Table A18, we get the fatigue strength factor F equals 0.87, the one that I mentioned, important for the delineation between low cycle fatigue and high cycle fatigue. And then, so all of the S ultimate and F will do the job for the SN curve, pretty much. Now I just need the stress concentration factor. Then the stress concentration factor, I have R over D. As you know, the stress concentration factor depends on the levels between the small diameter and the big diameter. So this is, it's all about the differences. And it's usually the stress concentration factor is a function of two parameters. The radius of curvature of the fillet divided by a small diameter. And that is, if it is not given, then we can assume it. Like you can see here, it's 62 mils as a radius of curvature for the shoulder. And the ratio of the big diameter to the small diameter, that's 1.15. So these two numbers, I can go to the figure and I get the stress concentration factor under steady loading, and that is 1.95. Now, that is not the same stress concentration factor under fatigue. It is higher because fatigue is a little bit forgiving. It leads to plastic deformation, and therefore it has the ability to smooth out some of the stress concentrations at the shoulders. And the parameter that does that is the Q, the notch sensitivity factor. So Q is, we have an empirical equation in terms of this square root of A. We have an empirical equation, and therefore when we compute it, we get 0.76. So 0.76, when we use it in the definition of the notch sensitivity factor, we convert the steady stress concentration factor, which is 195, to a fatigue stress concentration factor, and that conversion gives us 1.72. If you are stressed in time, just forget about the notch sensitivity factor. You say, well, I assume it is 0.8 or 0.9, and therefore I get that fatigue stress concentration factor to be such and such. So that's okay. Now we have the case of F, and therefore we got all the ingredients. Ingredients is that we need the A and B for the SN relationship. We need the stress concentration factor because that amplifies the fully reversed stress. So on the strength side, we determine S endurance prime. That is, S endurance prime is the smooth bar specimen. Endurance strength is half of the ultimate for steels. So we get 42.5. And then once we know the A and B from the equations I showed you earlier, we plug them in here, we get the fatigue factors. So we have the case of A and the case of B, case of C. These are all the fatigue factors. So you modify the endurance limit for the smooth bar to the endurance limit for an actual component. So you can see it got knocked down from 42.5 to 29.5, and that is the effect of surfaces. The effect of the first factor is a surface factor, and then the size factor is the second one, and then the load factor is one, and then the other factors we don't have information, so we just assume they're one, and that therefore we have now a new value for the endurance limit of the actual component that we're designing. All right, so having done that, then I can find from the F and S ultimate and SE, I can find the A and B values, and therefore we know now that the straight line equation is the power law for the fully reversed sigma. And N is given to me, 20,000. And then I know the A and B, and I know also the stress concentration factor. That gives me 28.87. That is the allowable fully reversed stress. And if I now include a safety factor of 1.5, then I even knock it down to 19.25. And therefore, I'm done, because once I know this, I know that sigma fully reversed must not exceed 29.67 F2, and then now I know sigma fully reversed, I can substitute and find the value of F2 and hence the value of F1. So this is a full and a quick review of a exam problem to show you the kind of the required that actually we're moving from just pure theory to an applied problem on power transmission here, and then it combines several ideas. The ideas is identification of whether you have low cycle fatigue, high cycle fatigue. Idea 2 is to find the coordinates of the points that delineate those. Idea 3 is to find the A and B constants to describe the linear relationship. Next idea is to find the stress concentration factor and account for the notch sensitivity, and that's it. So this is kind of the combination of ideas that we have for that particular example. All right, so I can just take a breath and see if you guys have questions at this point.
No questions about the problem.
Okay. Any other questions?
Would you be willing to post this?
You want to post the solutions to this exam?
If you'd be willing to post them, it was good practice for me with the midterm.
Yeah, I'll post this because I think we're getting close to the final, so I'll post the solutions.
Thank you.
Okay. All right. I have one more idea that I want to throw in here. And the idea is the following. It relates to fatigue, so we can just finish, everything about fatigue. Suppose now that in addition to the forces imposed by the gears, that we have the forces F1 and F2 you can see now that they're vertical, just purely vertical, bearing down on the shaft, right? So you have action R1, RA, and RB, no problem. What happens if we have real gears, as you'll see in this week and the following week? When you have real gears, then the force is transmitted through some contact line, and the contact line is never perpendicular in the vertical direction. It actually has a pressure angle. So every gear is designed with a pressure angle, usually is around 20 degrees from the horizontal. So the force is actually coming at an angle, right? So what do you do about this case? So if we have F1 and F2, you will have some kind of an inclination on the bearing down, not vertical down on the shaft, but at the end at an angle. Well, in this case, okay, we will have to decompose the force F1 and F2 to its components. So you have vertical component, would be F1, 10, 20, and then a horizontal component, which is the complement to that. So it's just vector decomposition, right? This is the next problem. So in the exam, we have another problem that turned out to be also on fatigue, because it is very much related to the design, power transmission system design that we are working on. So if you look at this problem, I have gear A, which is 60 millimeter diameter, and gear B is 300 millimeter diameter. Gear A has a force F1 with a pressure angle, 20, like you can see here. Actually 25, yeah. Let me make it a little bit bigger. Yeah. So this is 25 degrees, and this is 20 degrees, okay? So in this case, it's you have the middle shaft between the two gears is 75 millimeter diameter, but the shaft on the left is 40 and the shaft on the right is 42. And then we have keyways, like here on the shoulders. So the gear has to kind of be attached to the shaft with a keyway on the left and a keyway on the right. So this is now throwing in a little bit extra complication here. So the extra complication is that if I take the component of FB, the vertical component is going to be coming down, and FA will be coming down. The problem here will look exactly similar to the previous one. But if I take the horizontal component of FB, it has to balance the horizontal component of FA. In what sense? Well, it has to balance it in the sense that the shaft is going to be rotating at constant RPM, and constant RPM would mean that the net torque on the shaft is equal to 0. So if I take the FB and take the find the torque that FB induces on the shaft, it has to be the same but opposite to the torque induced by FA, right? So if you just go from point C to B, you have no torque, and then right at B, you have concentrated torque, let's say counterclockwise, and then between this point and A, that concentrated torque would remain constant. So you have a constant torque on the middle shaft, and then now you have another torque at point A, and that torque is clockwise, so it will cancel out the torque at B, and then you move on to the small shaft. You have no torque, and that explains why in the middle shaft you have to make it a little bit beefier, because it will have a torque on it in addition to the bending moment. So that makes the problem interesting in several ways. Number one, I would have the stress at any point will be composed of two parts. One is alternating, and the alternating will come from the moment. So I have to find a moment diagram going from 0 up to some value at A, and then up again at B, and then down to 0 at C. And then I'll have to determine which point is it A or B as my critical points. So that's the story with the alternating component, very similar to the previous problem. Now you add to this another steady component, because the torque, once it is induced, the shaft has to rotate at a constant RPM, then it will have to be steady. So there's no change in the torque with time. And therefore, the stress in the AB section that is caused by the torque is a shear stress, pure shear, and it is constant. So the moment is alternating, induces an alternating axial stress. The torque induces a constant or steady pure shear stress. So now, right, so now we see that the stress, it has to be dealt with in the same way as we did in failure theories. So now we have to combine the alternating stress and the constant stress using the concepts of failure, either distortion energy criterion, maximum shear criterion, Coulomb-Moore, and so forth. So usually we use the distortion energy criterion to do that kind of combination. So that kind of shaft is, you can see it is really, like this problem here is much closer to your final end goal in shaft design for power transmission, because it combines a number of elements. So if we go through it, the same old stuff is ultimate and SEALD, you look it up. The keyways now are a little bit different, because the keyways have different stress concentration factors from shoulders. So in theory, I have to find the stress concentration in the keyway and also in the shoulder, and figure out which is higher. So in the keyway, it depends on the R over D. for the way that it is kind of milled, and therefore I get from the table 2.14, and then it has one for tensile and one for shear is 3, and then the notch sensitivity factors, I get them from the figures, and therefore I can convert the steady stress concentration to fatigue stress concentration factors. So I do that for the keyway, I do this for the shoulder, I compare, and I find that the keyway is going to be more critical than the shoulder. And here now the story is similar. SE prime is computed, the fatigue factors, the ABC factors are computed. And now the new element is that we know now that we have a steady load caused by the moment M, and an alternating load caused by the moment. So M is going to be M sub A because alternating, and T is going to be the torque that is steady. And I combine them using the von Mises criterion that we use to find kind of the effective stress. So in here, that's kind of the end. Now the rest of it is just statics, so you have to be very good in statics so we don't make like mistakes with the statics, because we have two planes, one horizontal, one vertical, to find, and then the moment is taken as the vectorial moment by the Pythagorean theorem, because you have two planes essentially. So it can be kind of not complicated, but you just need to practice so we don't make mistakes. Like the statics part, it should be pretty straightforward, but there could be some mistakes in the numbers, and also the concept of the moment as a vector has to be understood. At the end of the day, that's what you design for. So when you go through a couple of examples like this, it will be clear to you how to design a shaft either for a system of forces from gears or pulleys that are inclined, like this kind of problem. This is more complex because it combines alternating and steady, or the simpler one that we discussed before, which is just an alternating type of loading on the shaft. So I think that's kind of my review today for the fatigue area, because we're moving on to next is gear design and how to combine gears with and assemble them with the shafts and to reach more comprehensive idea about design of power transmission systems. So any questions or comments?
Yeah, I guess I had a quick question. But mainly it's going to be, I know we're using some of the concepts from previous, like from the midterm on, but is it just going to mainly be on the new stuff that we've learned from the midterm?
Well, if you look at this final, you can see like these two last problems emphasize, one emphasizes fatigue, which is 4, and the other one is emphasizing power transmission design, which is here. And then we have another problem. Okay, let me see. Another problem that is going into gear design. So, which is what we're going to study the next chapter. So this is mainly on how to use gears and design. That was a bonus problem. So that's all from the second part. And then we have another problem that is on stress. So this is on a rotating ring, and the rotating ring it has a weight, And then because of the angular speed, you get tangential and radial stress, but you have a complicated function of the radius. So the question is that, determine failure. So this is on failure beyond the midterm also. So this one combines a little bit from before the midterm, a little bit after the midterm through the failure criterion, and then determining where the location of failure is going to be. So a little bit knowledge of where things are in that particular system. So these are all from the second part. And then we have a problem now of a lever and the force in the middle and 2 wires. And this part is about deflection. So the deflection is on Castigliano's theorem and statics, combination of those. And that was before the midterm, but as you could see in the midterm, we didn't really go deeper into Castigliano. So you would expect on the final also something like that. So it's not really elementary from the beginning, but it is on the right into when we got into the midterm. And then the first problem is a problem that has a design problem that has an eye bolt, and the eye bolt has a force here, and then he designed this. So this one has more on the first part. So I went like a longer response, but essentially the emphasis, as you can see, is on the second part, but then you have connections to the first part of the course. And the connections are not on the elementary part of the initially, but on the parts that are kind of strong, that you feel is strong, and then transitioning to the second part of the course. So I'm gonna post this exam solutions on the website right away, so you can have a look at it. It's just a guide, but it doesn't mean that the final is going to be like this, but it's going to give you the flavor of what level of problems or design problems that we are looking at. Okay, any other questions? Okay, so it looks like we did pretty good today. So I'm going to just stop here, and I'll have the this session also posted on our website as usual through the YouTube if you want to go back to it. Okay, so you guys, everybody's doing okay on the report, because I gave a lot of comments on the progress report. All of your exams are graded, the homework is graded. So we have only 2 weeks left. I think everybody should kind of push a little bit harder to finish the project right now, and then start to focus for the final. Okay, so I think we're going to stop here, and we'll see you guys next week.
Sounds good.
Yeah, so we'll see you later.
Thank you.
Yeah, bye-bye.